Last week, we introduced our new unit on atomic physics. It's called the nature of matter. And the first thing that we did was looked at the discovery of the electron. Does anybody remember who the guy was that discovered the electron? At least the guy that's given credit for the discovery of the electron? J.J. Thomson, yeah. 1897, so just over 100 years ago. 100 and, what would that be, 117 years ago, we discovered the electron. Prior to that, we knew about charge, right? Charge wasn't a complete mystery. We knew about positive charge, we knew about negative charge, how they responded to electric fields and magnetic fields. We just didn't know anything about where those charges came from. Thomson used an apparatus called the cathode ray tube. And the cathode ray tube has been around for probably 50 years, 40, 50 years, prior to 1897, used for a whole bunch of purposes. But in the end, nobody really understood exactly what was going on. The cathode ray tube in its most basic form consisted of or consists of a couple of electrodes inside this evacuated tube. We get a battery set up like this, which gives us a negative terminal right here and a positive terminal right here. By the way, what would this negative terminal be called? It's called the cathode. And we know that gets a little bit confusing with chemistry, but that's what we call it nonetheless. This would be called the anode, right? Now, we called it a cathode ray tube because there was this mysterious greenish glow that would come from the cathode toward the anode. Now, it would skip right through the anode because there's a little hole that we had set up in the anode. Come over here and hit the screen that was painted with a phosphorescent coating, causing the screen to glow wherever the cathode ray hit it. Nobody really knew what this cathode ray tube or cathode ray was. Lots of people said, well, maybe it's electromagnetic radiation of some type, right? Some kind of visible light or whatever. Maybe it's charged particles, but nobody really knew exactly what this was that was going from the cathode to the anode. So Thomson said, you know what, I'm going to figure it out. I'm going to find out what this is. What did he do to figure out what this was? Over here on the right-hand side, he introduced what? He introduced the magnetic field. It doesn't really matter what direction that magnetic field points. If it points the way that I have it drawn, that would cause these cathode rays to be deflected downwards, right? Thumb, fingers, palm. If the magnetic field is pointing out of the page, then our electrons don't know them, but at the time, these cathode rays would be deflected up in the opposite direction. They're exposed to this magnetic field. These guys, in this case, deflect downwards. Okay, that told them what? These beams, these unknown, mysterious beams that we call cathode rays, are really just what? Charges, yeah. Specifically, negatively charged particles. Didn't say anything about the subatomic nature of them. We didn't know anything about any of the properties of these negative particles other than the fact that they're negatively charged, by virtue of the fact that they're deflected downwards in this inward magnetic field. But Thomson says, you know what? I can do a little bit of analysis on this, because I've done this a million times before, where charged particles are going in magnetic fields, go in a circle. So let's say mv squared over r is equal to qvb. That's not new. I don't have to be a genius to do that. Lots of people have done that. Crosses off v, left with mv over r equals q times v. This is where he runs into a little bit of trouble. Do you know what m is? The mass of these negative particles, he doesn't know. The speed? No. R, yeah, he knows r. He can look at where they hit the screen based on where the screen glows. He knows what the value of r is, so we're 1 for 3. Charge, doesn't know that one, no. E, yeah, knows that. He introduced the magnetic field, so presumably he can easily measure what the value of that magnetic field is. That's still 3 unknowns though, right? 5 variables, 3 unknowns. So he does something else. He does something else, try to figure out what the value of the speed is for these negatively charged mysterious particles. Somewhere in between this section and this section, he introduces what? Good. A magnetic field that we have directed into the page here, and an electric field that's caused by these positive and negative plates. The magnetic field will cause these particles to be deflected downwards. So there's a magnetic force acting downwards and electric force acting upwards, right? Negative particles going through an electric field that's pointing downwards is going to cause the force to be opposite to that, upwards. Except that's an electric force, not a magnetic force. Sometimes one of these forces is bigger than the other. If the particle is going too fast or too slow, then one of these forces will be bigger than the other, and the particle is either going to be deflected upwards to here or downwards to here. We don't care about those particles. We care about the ones that go straight through, the ones that enter this main chamber over here straight on. What do we know about those two forces for the particles that are going straight through? They've got to be balanced, right? They've got to be equal to each other. So let's set Fe equal to Fm. Q times the electric field is equal to Q times V times the magnetic field. Q's cancel. Tells us doesn't matter what the charge is. Okay, we know it's negative, but it doesn't really matter what it is. In any case, if those particles go straight through undeflected, the speed is going to be equal to E over B. Now, what are we going to do with that? Well, those ones that went straight through into the main chamber, we know their speed. So now, instead of having 3 unknowns, now we only have 2 unknowns. We talked about on Thursday, before your grad retreat on Friday, the idea of a ratio here. We don't know 2 variables. Let's find a ratio between the 2. It's not great, but it's better than having nothing. So we rearrange this equation to solve not for Q, not for M, but the ratio of Q to M. Take the M over by dividing, the B over by dividing, and I get V over B times R. The value of that, which, by the way, you don't have to memorize. You ever had to find the value of Q over M for an electron? Given all the information you have on your data sheet, what should you do? What's the easiest way to find Q over M for the electron if you're given all the information already on your data sheet? Divide Q by M, right? Now, if you have to get it from this experiment, obviously you can't do that, but what was kind of special about that number that we got for the charge to mass ratio of these mysterious cathode rays that we now know are negatively charged particles? It's really, really big. Okay, it's really, really big. Basically, we're saying, look, if Q over M is big, then M must be small. And if this is so big that it's bigger than any other charge to mass ratio ever found, then the mass must be smaller than any other mass ever found, which means if it's smaller than the mass of an atom, it's got to be subatomic. It's got to be a particle that's inside the atom. Hence, the electrons floating around in the sea of positive charge. Now, we also talked real briefly about this acceleration chamber over here. We don't see a problem on that very often, okay, but from time to time we do. A little bit later today, you're going to see one on this first chamber. What do we do there? These charged particles accelerate. This is not unlike the last question on your electricity assignment that you just handed in. When these charged particles accelerate, it's like a car going down a hill. And what do we do when a car goes down a hill? EI equals EF. This time it's not gravitational potential energy, it's electric potential energy that's converted to kinetic. Now, we could solve for speed there. Why do we not like to use the speed here in here? Why is it not ideal to use the speed from this acceleration chamber over here? I mean, we could do it, which would eliminate the need for having a velocity selection chamber, right? So why do we not want to do that? Yeah, the speed that we get here, right here, isn't necessarily the speed the electrons are actually moving when they go through this, into this main chamber. Rather, that's the maximum possible speed. They might be going slower than that. If the energy conversion isn't 100% efficient, then the particles might be going slower. If they're going slower, it means we don't know how fast they're moving. We just know that that's how fast the fastest ones are moving. So if we got to use it, then we use it. But if we can get information from a velocity selector, then let's do that, because that gives us an exact speed, not the maximum speed. All right. We had some questions for homework on 756 and 758. Any issues with either of those sets of questions? 756, first of all. Going once, going twice. What about 758? I'm thinking number 3 on 758. Any others? No? All right. Let's take a look at number 3. I know that I was chatting with one person earlier today that was having a little bit of trouble with number 3. And as I was going through it, I remember thinking, yeah, you know what, there's probably going to be quite a few people that have trouble with this one. Just the way that it's set up here. Okay, conceptually, it's not crazy, but it just seems a little bit tricky mathematically. So let's do that. It says a carbon-12 ion has a charge-to-mass ratio of 8.04 times 10 to the 6. So this isn't a cathode ray tube, right? Because cathode ray tubes involve electrons. But it's close. It's the same thing, really, except that you're using carbon ions instead of a cathode ray tube. What do we call it, by the way, when we're using ions? As opposed to a cathode ray tube, it's a mass spectrometer, yeah. So it helps us, mass spectrometer helps us to identify properties of ions, which allows us to identify what the ion is. So we got carbon-12 going through here. It has a charge-to-mass ratio of 8.04 times 10 to the 6. By the way, what do you notice about that charge-to-mass ratio? It's way, way smaller, right? It's 100,000 times smaller almost than the charge-to-mass ratio of the electron. 100,000 times smaller. Okay, what does that tell you about the mass? It's a lot bigger, right? Of course. It's much bigger than the mass of the electron, which we would expect. We want to find a radius. We got a speed here, and we got a magnetic field, but we also have kilometers per second there. We got to pay attention to. Now, what I don't want you to do is just memorize the equation for Q over M. Okay, I don't want you to memorize any equations. You got a lot to remember in Physics 30 and even more in your other courses. Okay, don't memorize more than you have to memorize. Figure it out. Okay, we know that in the main chamber, we've got Fc equal to Fm. Hey, that's all you really have to remember. Fc equals Fm. You don't even have to remember that. Just picture it. Okay, and you should be able to get that. Okay, that gives us mv squared over r equals qvb. V's cancel. Okay, mv over r equals q times b. Now we want to rearrange to solve for r. R goes up, qb goes down, becomes mv over q times b. Now, what's the problem here? Okay, we got v easy enough. We got b easy enough. What's the problem? What's the tricky part of this? Do we have m and q? We don't. Do we have m over q? We don't. What do we have? We have q over m. So if we have 8.04 times 10 to the 6 is q over m, then m over q would be the inverse of that, 1 over 8.04 times 10 to the 6. Does that make sense? How many people got that? Good, good, excellent. So we got that number. Okay, whatever 1 over 8 equals, somewhere around 1.25 times 10 to the minus 6 or something like that. Multiply that by v, 150,000 meters per second. Divide that by b, 0.5. We should get the answer that's in the book now for that. 0.037 meters. Is that good? Does that make sense? Did anybody do that a little bit of a different way? And you get the right answer? Wilson, what did you do? Okay, yeah, that's fine. Okay, so Wilson said, okay, that's fair enough, Wilson. That might actually be a little bit easier mathematically to do. So rearrange this to solve for q over m, v over vr, and then sub in the value that we're given for q over m, and then rearrange it to solve for r, is what you're saying. Yeah. Yeah, I don't know if it's easy or not, but it's a good method. It works. All right, if we're okay with those practice problems, we're going to assign a few questions for homework tonight. Check and reflect questions on page 760. I'd like you to do the following ones, please. Number 1 and 3 to 9. So basically 1 to 9 except for question number 2. We're not going to give you a chance to work on those right now, but they should go fairly quickly. what I'd like you to do right now is have a look at a couple multiple choice questions. The first one being number 146, question number 146. We'll have you submit that, by the way, as multiple choice question number 1. Submission one, please. Okay, let's have a look, guys. It says a cathode ray tube are used in television and computer screens. They're set up as follows, or as shown below. Okay, and you got the basic setup here. This is looks a little bit different than the diagram that I showed you, but that's okay. Don't worry about that. You got a cathode, you got an anode here. Then you got deflection coils here. So that's essentially the main chamber of the cathode ray tube, where you can deflect the beam of the electrons in any direction you want. So you get deflection coils horizontally, vertically, okay, which allows you to deflect it upwards or downwards or left to right, depending upon where you want to deflect it. That would be useful in a TV, right, to be able to deflect it wherever you want so that it hits the screen in the right place. They don't have drawn here a velocity selection chamber. That's okay. Okay, it just simplifies it for us a little bit. Now, we want to find out what speed the electron hits the screen at. Or at least, I'll give you a little hint here. What's the maximum speed at which the electron hits the screen? We only have information about the acceleration chamber right here. That chamber where I said we don't actually analyze all that often. Now it turns out in the first question we see here, we do analyze it. EI is equal to the EF. The initial energy is potential energy. It's like that car at the top of the hill. It equals kinetic energy, okay, the car at the bottom of the hill. QVI is equal to 1 FMV squared. We know what Q is. We know what V is, 2,500. Okay, M is the mass of the electron. Solve for speed. When you solve for that, you're going to get 3.0 times 10 to the 7 meters per second. Now, I want you to be able to solve this question. I want you to do it like we've done it. But if you can't, if you're struggling, if it's a test and you're just, I don't know what to do. I'm at a loss. My mind is mush. I don't know what to do for this. You can get the right answer for this question, even if you don't know what to do. Okay? I would rather you get the right answer because you know exactly what to do. We know, though, that D is not going to be the answer. How come? Because it's greater than 3 times 10 to the 8. Now, there's only one option here that's greater than 3 times 10 to the 8, which means we can eliminate only one, right? Well, odds are, if you get a number for speed that's greater than 3 times 10 to the 8, it's because you've done what? Well, yes. Made a mistake, yes. Could you be more specific with that mistake? You've probably forgotten to square root it. Okay, so if you see 8.8 times 10 to the 14 and you've forgotten to square root it, odds are the actual answer is the square root of that. So if you square root that, what do you get? 3 times 10 to the 7 meters per second. So that's not going to work for us all the time, right? We're not always going to have the option, the ability to look at this and say, oh, wait, there's only one that we can eliminate. But if we square root that, we can get the answer. Okay? Even so, that's still no guarantee that it's the correct answer. But if you're struggling or you're pushed for time or whatever, okay, it's a second option that might allow us to get an answer, save a little bit of time or something like that. Okay, let's take a look at the next set, which is 148 and 149, please. They both go with this information that you see right here. I'm going to ask you to submit those, please, 148 and 149, just under one submission as multiple choice 1 and numerical response 1. Multiple choice 1 and numerical response 1, please. All right, guys, let's take a look at it here now. Everybody that submitted it, although it's not very many of you, have got the right answers here. That's good, at least. This one says a scientist places 10 grams of this radioactive sample, radium-224. You guys don't even really know what that is at this point. You will later on in the unit. That doesn't matter. Okay? You don't have to really know what it is. All you have to know is that something's being emitted here. Some kind of charged particle is being emitted from this source. What is it? It's charged. Doesn't matter. It's not a cathode ray tube, but it's like a cathode ray tube. Okay? Kind of like a cathode ray tube. But in the end, it gets a little bit confusing here because of the way this is set up. Okay, we've got a potential difference across a couple plates here. Okay, that creates an electric field, but then we've got these coils that create a magnetic field. What chamber of the cathode ray tube would this be? If it was a cathode ray tube, sorry? It would be the velocity selection chamber, right, where the electric force will balance out the magnetic force. But then it goes on to say that when the electric field is eliminated, So when we take away the electric field, what do we got? We got a main chamber, right? So it's not going from the velocity selection chamber to the main chamber like it does in a traditional cathode ray tube. Rather, the velocity selection chamber becomes the main chamber. Does that make sense? We have an electric and a magnetic field where they balance. Then we have just a magnetic field where they go in a circle. So with that understanding, let's take a look at the questions here. The particles in the undeflected beam are going how fast? Well, let's treat it like the velocity selection chamber, where we know that Fe equals Fm. Q times E is going to be equal to QVB, and we're going to solve for V. But we got a bit of a problem here. It's not huge, but a bit of a problem. What are we going to do? We don't know what E is. Well, what's the electric field between two parallel plates equal to? You guys know this, right? E is equal to delta V over delta D. So you've got delta V. It's 5.3 times 10 to the 5. You've got delta D, which is 0.30. Okay, that gives us an electric field. I'm not sure what that works out to be. Okay, we divide that by the magnetic field of 0.7 Tesla. And what do we end up getting there for the speed? I'm going to guess 10 to the 5-ish meters per second, 10 to the 6. What's the final speed there, guys? Sorry? 2.5 times 10 to the 6. That's right. I remember that now. Which we express, since we're looking for A, B, C, 2, 5, and 6. Leave the last one blank. All right? Is that good? All right, let's take a look at the second part of this now. Using the charge to mass ratio of the particles, the scientist determines the particles to be what? Well, let's get the charge to mass ratio. To get the charge to mass ratio, we've got to use the main chamber. In order to do that, we've got to get rid of the electric field. So you've got just a magnetic field now, where Fc is equal to Fm. We're going to say mv squared over r is equal to qvb. These cancel. mv over r equals q times b. Let's solve for q over m. Okay, does anybody have the value of q over m there? Okay, we've got all the data. I just don't want to go through the process of calculating that. What is it? .0095 times 10 to the 7. Okay. Coulombs per kilograms. All right. What do you notice about that one? It's a bigger number than the last one that we saw, but it's still dramatically smaller, about 10,000 times smaller than the charge to mass ratio of an electron, right? So when you go and look at our options, we know it's not going to be an electron because it's 10,000 times smaller. Even if you didn't remember the charge to mass ratio of the electron, you could figure it out by dividing Q over M. You would have gotten 1.76 times 10 to the 11. Okay, so that one didn't work. What about B, a neutron? Why am I crossing off B without even calculating a charge to mass ratio? Because it's 0, it has no charge. Proton, alpha particle. Divide Q over M for both of them. Okay. Both of them are going to give you a value that's less than 1.76 times 10 to the 11. The alpha particle, I believe, is the one that gives you this value right here, 1.0 times 10 to the 7. So that means it's got to be D, the alpha particle. That make sense? All right, guys, let's move forward here now. In 1897, J.J. Thomson discovered the electron. He found the charge to mass ratio, but as we know, he couldn't find the charge and he couldn't find the mass. Let's fast forward a few years. 20th century now, Robert Millikan says, you know what, that's great. We know that the electron exists. We know what the charge to mass ratio of the electron is. That's a lot more than we knew 10 years ago. But Millikan says, I think I can go further. I think I can find the charge of the electron, and I think I can find the mass of the electron. So he sets up an experiment called the oil drop experiment. In its most basic form, it looks like what we have on the right-hand side here. We've got two charged plates, charged from this battery that we see right here, this being the positive side, this being the negative side. It's going to make my top plate positive, my bottom plate negative. Now understand that this is inside this big chamber that doesn't allow air currents to cause any problems or anything. Okay, we're just simplifying it a little bit just so the diagram isn't quite so cluttered. Two charged plates, positive and negative. Now what we do is inject tiny little oil droplets in there. We do that by using what we call an atomizer. Okay, you spray cologne or perfume on yourself. Okay, and you use what we call an atomizer. You take a liquid and you turn that liquid into tiny little microscopic particles, droplets. Now, they're not the size of atoms. We're not making them that small. We just call it an atomizer because we're making them really, really small. So we spray this oil droplets in between these plates, kind of like you spray perfume or cologne onto yourself. These little oil droplets, some of them are neutral, but some of them become charged. Some of them get a negative charge and some of them get a positive charge because of friction. They rub against each other. They rub against the nozzle of the atomizer. They rub against air. Some of them become charged. In fact, we can even give them charges, which we won't talk about how we do that or why we do that. But bottom line is, these oil droplets, a lot of them are going to be positively charged. A lot of them are going to be negatively charged. Each of these oil droplets experiences two forces. They are the gravitational force, which is going to act down on both of them. What's the other force that acts on these oil droplets? Look at the situation. Okay, you don't have to memorize anything. You don't have to have ever seen this before to tell me what the other force is that acts on these oil droplets. Besides gravity, it's got to be what? It's got to be an electric force, right? There's two charged plates that causes an electric force upwards on this one and downwards on this one. Now, what's going to happen to that positive particle as a result of both of those forces? Not only is it going to fall down, it's going to accelerate down. And it's going to accelerate down at a rate of acceleration that is greater than 9.81. Because gravity, combined with another downward force, makes it speed up at more than 9.81 meters per second squared. How much bigger? Depends upon how big the electric force is. What's going to happen to this one? There's a number of things that could happen to this one. Okay, what's one thing that could happen to this negatively charged oil drop? Yep. Okay, it could be in equilibrium. It could remain suspended if what happens? Okay, if Fe is equal to Fg, then it could be suspended. Now, if Fe is equal to Fg, it doesn't have to be suspended. It could still travel up or down, but if it's going to travel up or down when the forces are balanced, it's going to be moving at a constant speed. Right? Newton's first law says an object at rest remains at rest until acted upon by an unbalanced force. An object in motion continues in motion at a constant velocity until acted upon by an unbalanced force. So, if these two forces are balanced, then we know that it's either going to be suspended or traveling up or down at a constant speed, not accelerating. If Fg is bigger, then it's going to accelerate downward at a rate that's less than 9.81. If Fe is bigger, it's going to accelerate upward. Its rate just being determined by how big Fe is. Let's focus on this particle right now, and specifically on that particle when it's either traveling at a constant speed, up or down, or suspended. Chase, I think it was, just told me that in those situations, Fe will be equal to Fg. Don't get that mixed up with something that lots of people in the last 19 years of my career have gotten mixed up with. What do people want to do here? They tend to want to make this the velocity selection chamber of the cathode ray tube. They tend to want to set Fe equal to Fm. If you look at this diagram, where do you see a magnetic field? If you try to memorize this, then there's a pretty good chance that you will get this mixed up with a velocity selection chamber. If you picture the diagram, if you visualize a diagram in your head when you're doing this problem, then you almost can't get it mixed up. You almost can't set it equal to the magnetic force because you don't see a magnetic field there. You can't put a magnetic force in logically when you don't see a magnetic field. So Fe equals Fg for the particles that are suspended or traveling at a constant speed. The electric force is Q times E. Remember, electric energy was Q times V. Force, QE. Magnetic force, M times G. Solve for Q. Now, just so you know, sometimes we're not given the value of the electric field. Sometimes we got to find that. But because we have two parallel plates, it's pretty easy to find. Delta V over delta D. Most times in my experience, you've got the value of E in these questions already. But if you don't, this is how you're going to find it. So what have we just found? What's Q stand for? Charge. Charge of what? Charge of an electron? Charge of an oil drop. All we found right now is a charge of an oil drop that we can physically see with our eyes if we have a magnifying device, right? You have to look at this through a system of lenses so that you can magnify it, but with this system of lenses, you can see it just fine, okay, with the naked eye. Well, with lenses, I guess. So what do? We repeat it, and then we repeat it again, and then we do it again, and then we do it again, and then we do it again, several hundred times, so that we get the charges of several hundred different oil droplets. And this is what we find. One of the oil droplets might have a charge of 3.2 times 10 to the minus 18 coulombs. Another one might be 4.8 times 10 to the minus 19 coulombs. Another one might be 9.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 17 coulombs. 1.6 times 10 to the minus 19 coulombs. 6.4 times 10 to the minus 18 coulombs. Whatever. What do you notice about all of these? Every single one of them, they're all multiples of this. If we multiply this number by 20, I should say, we get this one. If we multiply it by 3, we get this one. If we multiply it by 6, we get this one. We multiply it by 100, we get this one. We multiply it by 40, we get this one. All of the oil droplets have a charge that is a multiple of 1.6 times 10 to the minus 19. That leads Millikan to two conclusions. One, there is such thing as an elementary charge. In other words, there is a smallest possible charge. You can't get smaller than that. You do this 500 times, and you get all these charges that are multiples of 1.6 times 10 to the minus 19, but nothing smaller than 1.6. The logical conclusion from that is that that's the smallest one that you can have. Which, by the way, since Thomson already said the electron is a fundamental particle, well, that must be the charge of the electron as well. The second conclusion that he drew from this, charge is quantized. What does the word quantized mean? You don't even necessarily have to know what that word means coming into class today. Okay, look at this and tell me what quantized means. Yeah, levels, like, yeah, certain allowable values. When I walk up the stairs, my energy is quantized. When I'm on the ground, I have 0 joules. When I'm on the first step, I have 100. When I'm on the second step, I have 200. On the third step, I have 300. My energy is quantized. There's only certain allowable energies. Charge is quantized. You can only have 1.6 times 10 to the minus 19 or a whole number multiple of 1.6 times 10 to the minus 19. Does that make sense? Now, real quickly here. Millikan has just found the charge. How do we find the mass? This is easy now that we've got the charge. Use the ratio, good, right? We've got the charge to mass ratio is 1.76 times 10 to the 11. Thomson did that, right? If Millikan finds the charge, then we can find the mass pretty easily mathematically, right? We don't have to do a new experiment to find the mass. So, who was it that discovered the electron? Thomson. Who found the charge to mass ratio of the electron? Thomson. Who was it that found the charge of the electron? Millikan. Who was it that got the mass of the electron? Let's give them both some credit for that, Thomson and Millikan, right? Because if we don't have the charge, we can't get the mass. If we don't have the charge to mass ratio, we can't get the mass. We need both of those guys to get the mass, right? So charge to mass, Thomson, charge, Millikan, mass, Thomson, and Millikan. Let's do a problem here. The question on page 763 says an oil droplet of this mass is suspended. That's good, because those are the easy problems, easier, I should say, when it's suspended. We have an electric field pointing downward. How many electrons has the oil droplet gained or lost? Let's draw it out here. All right, we have an electric field pointing downward. We have an oil droplet. Now, that oil droplet, we don't know whether it's positive or negative, but we do know that the force of gravity must act down, and we know that the electric force must act up. How do you know electric force has to act up? It doesn't tell us that. If it's suspended, they've got to balance each other, right? Let's set FE equal to FG. Let's set Q times E equal to M times G. Let's solve for Q. I get mg over E. The mass is 8.2 times 10 to the minus 15 times 9.81 divided by the electric field, which we've got here, but if we didn't, we would solve for it using delta V over delta D. What do we get for the charge there? 8.04 times 10 to the minus 19 coulombs. All right, that's my charge. Now I'm looking for the number of electrons gained or lost. How do you find a number? Physics 30, how do you find a number? Total divided by the amount for 1. In this case, 8.04 times 10 to the negative 19 divided by 1.60 times 10 to the minus 19. What do we get there? 5. Now, gained or lost? Gained or lost? That's the tough part of this question. 5 electrons gained or 5 electrons lost? What's the charge of this oil drop, positive or negative? How do you know it's negative? Good. If the electric field is down, in order to experience a force up, it must be negative. If it was positive, the force would be in the same direction as the field. So it's got to be negative. If it's negative, did it gain or lose electrons? If you're neutral and you lose electrons, you become positive. So this must have gained electrons. Does that make sense? All right. I'm going to give you about 1 minute or about a minute and a half to work on these questions. See if you can get the first one done. And then I want to do one more example with you, okay? All right, guys, let's move on. I know you didn't have a lot of chance to work on those problems. Finish those up for homework tonight, please. I just want to do one more example. But before I do that, I've got to show you what to do for that example. If we're looking at a charged particle chase that's accelerating, and that could include the negative charge, okay, if one force is bigger than the other, or it could include the positive oil droplet, for which it has to be accelerating because both forces are downward. Doesn't matter. If it's accelerating, then we're going to say F net is equal to the sum of the forces. That's going to be Fe plus Fg. So they don't balance. There's a net force. And that force is equal to the two forces that we have combined. Now, the net force will also be equal to m times a. Electric force QE, gravitational force m times g. At this point, we just plug numbers in and solve for what we're looking for, typically charge. Mass times acceleration, electric field, mass times acceleration due to gravity. Just be careful now. You pay attention to whether you've got a positive or negative values, right? If the gravitational force is down, then make this negative. If the electric force is downwards, then make it negative. If it's upwards, then make it positive. Okay, if the acceleration is upwards, make it positive. If it's downward, make it negative. Every question is different. Look at the question and identify what each of these are, up or down. If they're up, make them positive. If they're down, make them negative. Let's take a look at one more example here, and then we'll wrap it up for the day. 764 says a tiny sphere of this mass is placed in this electric field. It's downward, so we're going to circle that. This here has 10 excess electrons. That means the charge will be 1.6 times 10 to the minus 18 coulombs, right? 10 times the charge of an electron. We want to determine if it will accelerate, and if so, which direction. Let's assume that it does accelerate. Let's find the acceleration. If we're correct in our assumption and it does accelerate, we'll get a value for that. If we're wrong in our assumption, what will we get for A? If it doesn't accelerate, what's A going to work out to be? 0. Let's draw a picture here. Okay, here's our two plates. We have a charge that is negative. We know it's negative because it has 10 excess electrons. Gravity is going to act downwards. We know the electric field acts downwards. That must mean the electric force acts which way? It's a negative particle, force acts, Noel? Up, opposite to the field. Now, we don't know that those balance, but they might. Let's say F net is equal to the sum of those forces. We get the mass here is 8.2 times 10 to the minus 15. We're solving for A, so we don't have to put in a value, a negative or a positive for that one. G is 9.81 plus, what's the charge here? 1.6 times 10 to the minus 18 times E is 1 times 10 to the 5. All right. What do we do for gravity, positive or negative? Because it's acting down. What do we do for the electric force, positive or negative? Positive because it's up. Even though they didn't tell me the electric force was up, we figured out that it was up. Or at least Noel figured out that it was up. I think it was Noel. Yes? Because the electric field is downward and it's a negative particle. So the force has to be opposite to the field. Okay, we solved for the acceleration there. I don't know what it is, but it doesn't work out to be 0, which means, yes, there is an acceleration. And if so, which direction? Well, you get a positive or negative value for that, Chad? Since it's a positive acceleration, which way does it accelerate? Upwards. You're going to work on a couple more questions here. That's quite a bit tonight, guys. You're going to end up with about 10 or 11 questions for homework tonight with the check and reflect combined with the practice problems on the oil drop experiment. Do your best, please, to get them done. You're going to find that these get a tiny bit tricky, not because in concept they're hard, but the direction is a little bit hard. Okay, the idea of, is the electric force up or down? Draw the picture. Drawing the picture really helps you with that direction. It really, really does. If you can work through that, these questions aren't that bad and they shouldn't take you all that long. All right? So practice problems on 764, practice problems on page 763 if you haven't finished those. And of course, we've got the check and reflect questions that were assigned earlier today as well. That's it.